Swayam Prabha. Digital India. Educated India.
Hello, welcome to Module 3, Week 2 of our course on Introduction to Dynamical Models in Biology. In this module, I will introduce you a new concept, that is steady state, and how to analyze the steady state. Analysis of steady state is very crucial in understanding dynamical systems. And there are well-developed mathematical formulations to do that. We will primarily try to understand the concept of steady state using intuitive techniques. Let us start with some basic idea, and I will introduce a concept of direction field at the beginning. Let us take the old model of spread of infectious disease. So what was the OD? X is the fraction which is infected with the disease. So dx dt, there is a rate of change of population infected with the disease, is equal to r into x into 1 minus x. So we want to analyze it using the concept of direction field. Let us see how to do that. The first thing I do, I plot t time in the horizontal axis and x in the vertical axis. So let us take a time point, for example t equal to 0, and at that time let us consider x is equal to 0.2. Notice one thing in my plotting region. Although x can never be negative, I have also shown negative values of x in this vertical axis. So 0 is here, positive values are in this direction, negative values are in this direction. I have drawn this so that when I will draw direction field, some interesting phenomena we can see here. So if I take a point t equal to 0, x equal to 0.2 and show it in this plotting region, then that will be this red dot. T equal to 0, x equal to 0.2. Now let us calculate dx dt at that time point and at that value of x. So dx dt is equal to r into x into 1 minus x. I have already written r equal to 1. So put r equal to 1 into 0.2 into 1 minus 0.2, that is 0.8, and the multiplication gives you 0.16. Now at that red dot in my plot, let us draw a blue arrow that I have shown here, an arrow having a slope which is equal to dx dt. So here at that point dx dt is 0.16, that comes around 9 to 10 degree angle. So put a arrow having an angle of 9 or 10 degree based on this dx dt. And notice the arrowhead is pointing up because with time dx dt is changing in the positive direction because I have a positive value here. So what I have shown here in the graph, I have taken a point at 0.2 in this space of x versus t, and then I have drawn an arrow there having a slope equal to dx dt at that point. Let us take another point. For example, t equal to 5 and x equal to 0.2. Let us calculate what is the value of dx dt at that point. R is again 1, x is 0.2, 1 minus 0.2, that is 0.8. You don't have any t term in this equation. That means this is not affected by t. So obviously I get the same value dx dt equal to 0.16. Let us put that point in this space and put an arrow having a slope 0.16. So that's I have done here. You have a point at 5.2, that is time is 5, x is 0.2, and there I have drawn an arrow having slope 0.16, that is equivalent to almost 9 degree. If you notice, this arrow and this arrow are actually parallel and their slope are same. That is because the ODE does not have any t term on the right hand side, and only the difference between these 2 points is that time has changed. In case of the first point, t is 0. In the next point, t is 5. But x has remained same at point 2. So as the right hand side only has x term, does not have any t term, the slopes of both the arrows are same. Let us take another point somewhere else. For example, at 2.5, that I have shown here, 2.5, and calculate dx dt there. It will be 1 into 0.5 into 1 minus 0.5. So if you multiply, it will be 0.25. Let us put an arrow there. Obviously, arrow head will be pointing up because 0.25, I have a plus sign there in the dx dt. So the slope of that line will be 0.25 as I have calculated. It is equivalent to almost 14 or 15 degree. So I have drawn a arrow here pointing up, having a slope 0.25. So what I have done, I have a t versus x space in which I have taken some point, and at those points I have calculated dx dt, the slope as per the ODE. Once I have calculated the slopes, I have drawn arrows with arrowhead, appropriate arrowhead on those points having the appropriate slopes as calculated from the derivative. I can extend this further. What I can do? I can divide the whole space of x and y. Suppose this is x and t. This is my space x and t, and I can divide it in equal grids like this. So I can divide in equidistance grid, and each of these grid point, these are the grid points, I can calculate dx dt as I have done earlier, and then I can draw arrows. That's what I have done here and shown in this plot. This is t, this is x. We have divided in equidistance grid. I have not shown the grid line for clarity. And at each of these grid point, I have calculated dx dt and drawn an arrow. So for example, this one you have seen, this is a grid point with 0.2. This is another grid point with 2.5. This is another grid point with 5.2. And each of these grid point, there is an arrow. The slope of the arrow is equal to the derivative of the dependent variable, that is x, at that point. This whole thing, this diagram with arrows in the dependent variable and time space, x and t space, is called direction field. For any given ODE, you can draw this direction field. Let us explore this direction field a bit more. Notice that when x equal to 0, your arrows are all horizontal. Horizontal arrows are coming because the slope at those positions is equal to 0. That means dx dt is equal to 0 at those positions. You have another value of x equal to 1, where all arrow at any time point you can see are horizontal. Here also dx dt is equal to 0. In between 0 and 1, the arrows are pointing up, and they are reaching towards, from 0 to 1, they are moving towards 1. What are they telling? Let us see. Let us take a point, for example, at time 0, let us take a point 2 here. So that is 0.2 for x at t equal to 0. The interval between these two grid points is 0.5. So if I start at this 0.2 position at t equal to 0, after 0.5 time, I will reach this point following this arrow. Then if I increment time further by 0.5, following this arrowhead, I will reach here. Then incrementing time further, using the same arrowhead, I will reach there. Then if I keep on following these arrows, and if I keep changing time with increment of 0.5, I will keep on following these arrows, and eventually I will reach 1 when the arrowheads will become horizontal. and I will keep moving along these as the slope remain equal to 0. So what I have done, I have started with the initial value at t equal to 0, I was at point 2, and then I have followed successive arrows and their direction to move through time and in this x versus time space. I have drawn it cleanly. You can see this is the line. This line is called integral curve. In fact, we have got this integral curve by integrating a numerical method. The method I have used here is based on direction field and is sometimes called graphical method. Graphical methods are very useful when you cannot integrate a particular ODE. Just looking at the graphical representation of direction field and the integral curve, you can get a quality behavior of the system. Let us take another initial point t equal to 0, x is 0.5, and then if I keep on following the successive arrows, then I will get another integral curve as shown here by the green one. So why I am discussing about integral curve and direction field? If you look into this direction field, I have two places, x equal to 1 and x equal to 0, where the direction field's arrows are horizontal. That means dx dt is equal to 0. When I start at an initial value of x 0.2, I move along this integral curve and eventually land up at this dx dt equal to 0 at x equal to 1. Similarly, when I start at 0.5, I follow this green line and eventually reach x equal to 1, where dx dt becomes 0. So I have two value of x where dx dt equal to 0 and the arrows are horizontal. These two values are called steady state of x. These are steady state because the dependent variable x is not changing with time and constant for these values. If you are at those values, the system will not change with time, it will stay there. So that's why these two values are called steady state. So by mathematical definition, if I have a ODE which is dx dt is equal to function of x and t, generalized way I have written, then the steady state is where dx dt is equal to 0. Now how should I find that steady state? So suppose I have been given a function dx dt is equal to f of xt, so I will put that equal to 0. Then I will simply do an algebra that f x and t is equal to 0. I will separate out x and t so that I get the value of x for which dx dt is equal to 0. Let us see an example. We will take the example of logistic growth. So the model ODE is dx dt is equal to r into 1 minus x by k into x. X is the size of the population. So the initial value of x is x naught, that is 100. The rate constant for growth of the population is 0.5 per minute, and k, the carrying capacity, is 10,000. I want to find out the steady states for this system. That means I want to find out the values of x for which dx dt will be equal to 0. How I use algebra to do that? By definition, at steady state, dx dt is equal to 0. That means r into 1 minus x into x is equal to 0, because that's what is the ODE telling me. Now once I have this relation and r is a non-zero thing, so r is non-zero, that means either x equal to 0 or 1 minus x by k is equal to 0. It is simple algebra. So that means if x equal to 0, dx dt will be 0. So that is my one steady state. Simply I got it. Now the other option is 1 minus x by k can also be 0. Then also dx dt will be 0. So when 1 minus x by k is equal to 0, I can separate out x and everything else. That becomes x by k equal to 1. That means x equal to k. So what I have got? I have two steady state for this logistic growth model. One is x equal to 0, one is x equal to k. For both these values, dx dt will be 0. Now you have given me that k is 10,000. That means the population has two steady state, one at x equal to 0, other one as k, that is 10,000. So if your population is already at 0, that is x equal to 0, the population will remain like that. That's true. If you don't have the organism, then what will grow? If your population is at carrying capacity, that is 10,000, that is another steady state. So if you have already reached the carrying capacity, there will be no further growth, so it will remain at steady state. So this system has two steady state, and using simple algebraic separation, we can find out the values of x for which we have the steady states. Now notice one interesting thing. For both the steady state, there is no role of rate or constant for growth, that is r. So the steady states are independent of rate constant for growth. They only depend upon the carrying capacity. So if I jot down the key points, what I have here, in this video, we started with discussion with direction field. Direction field is a qualitative way to see how the ODE behave in time versus dependent variable space. So what you do in case of direction field, suppose you have a ODE involving dependent variable x and independent variable time. So you plot x versus x, t space. We divide that space in equal size grid, and at each grid point we calculate the derivative of x, that is dx dt, and then there we draw some arrow having the slope which is equal to dx dt. So if you fill the whole space with these arrows, we will have a direction field. And if you look at the direction field image, it is almost like the field images that you have seen in physics textbooks for magnetic field or electrical field. So once you have the direction field, you can decide your initial position, that is t equal to 0, the position, the value of x, and then you can follow one arrow after another as the arrow point from the initial position and join those dots to give an integral curve. That curve will give the time evolution of x, the way x will keep on changing with time. This is equivalent to what you have got by integrating and then plotting the function of t for x, or you get by numerical solution. So direction field gives me a visualization of evolution of x with respect to time, the dependent variable with respect to time. Now in this direction field, there are places where dx dt is equal to 0. The value of x for which the derivative of it is equal to 0 is called steady state. At steady state, the system does not change. For example, the fish model, when the system, the population is in steady state of population equal to 0 or 10,000, the carrying capacity, the population will not change. So the derivative of population size at that point with respect to time is equal to 0. So a system can evolve from a non-steady state position to a steady state position. And at steady state, it will not change with time. We can calculate the steady state algebraically. And remember, a system can have one or more steady state, and you have to find them and understand the behavior of those steady state. In another module, we will discuss different behavior and properties of the steady state. Today we end here. Thanks for watching. See you in the next module.